This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is the moment of inertia of standard sections and composite sections. The moment of inertia of composite sections. If the composite section means or the composite figure, it is a figure with the combination of several or number of regular sections. Here the regular sections according to the subject, they are rectangle, square, triangle, circle and semicircle and so on. These composite figures first of all divide into some number of segments in such a way that it consists of minimum number of segments of regular sections, minimum number. Then find the moment of inertia of each section about the given axis and the sum of the moment of inertia of all the sections about any axis is representing the moment of inertia of the composite sections about the same axis. Okay, by using these principles, we can determine the moment of inertia of composite section. Here, composite section means it is a combination of regular sections such as rectangle, square, triangle, semicircle, circle, and so on. Now, before discussing the moment of inertia composite sections, first of all, we will discuss the moment of inertia of regular sections about its central axis or about its basis. Here the procedure of determination of moment of inertia of composite sections. First observe the given composite figure. If the figure is symmetrically about the x-axis and the y-axis, then take that axis as reference axis to determine the moment of inertia of composite sections. If the figure is not at all symmetrical about the x-axis and y-axis, then the axis which is passing through the bottom of the figure is taken as x reference axis. The vertical line which is passing through the extreme left of the given figure is treated as the y-axis. After identify the reference axis for the composite figure, split the given section into the regular plane sections or the plane area such as rectangular, triangular, circular, semicircle and rectangle and so on, and find the position of center of gravity of each section. Find the moment of inertia of these areas about their respective central gravity and centroids parallel to the reference axis what we earlier identified. Then transfer the moment of inertia of that entire area about to reference axis by using the parallax theorem, that is IAB is equal to IG plus AH square now, where IAB is representing the position of the reference axis. Okay, according to our discussion, that is the treated as the x-axis and the y-axis, and IG is representing the position of that is moment of inertia of each section about their central axis. Area is representing area of each section, and H is representing the position of the centroid of that plane section with respect to the reference lines. Now, the moment of inertia of entire section is obtained. The algebraic sum of the moment of inertia of each section about the same line. That is, Iyy of the composite section is equal to Iy1 plus Iy2 and so on. These are nothing but representing the moment of inertia of each section about the y-axis. By using these principles, we can determine the moment of inertia of composite sections about the y-axis, similarly about the x-axis. If we required the moment of inertia of that whole sections about the z-axis, that is the polar moment of inertia, which is equal to the sum of the moment of inertia possessed by the object about the x-axis and the y-axis. These are the steps generally followed to determine the moment of inertia of composite section about the reference axis. Now, before discussing, we'll find the moment of inertia of certain regular figures. A regular section means already I told it may be the rectangle or hollow rectangle, a triangle, circle, semicircle, quarter circle, and so on. The moment of inertia of rectangle about their central axis. Here the central axis are the axes which are passing through the centroid of the rectangle. The centroid of rectangle is with respect to the base, it lies at a distance of d by 2 from the reference left reference lines b by 2 and d by 2. That is half of the breadth, half of the depth where they are intersecting. That is treated as the position of the centroid of the given plane. So, according to the basic principles earlier we discussed now, the I-axis is equal to, that means the moment of inertia of rectangle about the x-axis. That is the x-axis means nothing but the central axis which is passing through the centroid and parallel to the x-axis are the Argentinal lines, which is equal to BDQ by 12 now. Similarly, about the y-axis is equal to DBQ by 12 now. And the moment of inertia of rectangle about its base is given by BDQ by 3 now. We have to remember this fundamental values of moment of inertia about the x-axis and y-axis. Similarly, for the cutout for hollow rectangle, the moment of inertia of hollow rectangle is obtained the difference of moment of inertia possessed by the outer rectangle, that is the main rectangle, and cutout rectangle, which is equal to BDQ by 12 minus of small letters BDQ by 12, where capital B is representing the breadth of the main circle, main rectangle, D is representing depth of the main rectangle. Similarly, small b and d is representing breadth and depth of cutout circle, cutout rectangle. So, I-axis is equal to, that is moment of inertia possessed by the hollow circle about the central axis parallel to the x-axis given by capital letters BDQ minus of small letters BDQ by 12. Similarly, I-y is equal to capital letters DBQ minus DBQ by 12 and so on. Now, third triangle, the moment of inertia possessed by the triangular sections about the central axis, that is the which is passing through the centroid and parallel to the base, it is equal to BHQ by 30, where B is representing the length of the base, H is representing the height of the triangle. Similarly, the moment of inertia of triangle about its base is given by IAB is equal to BHQ by 12 now. Similarly, for the circle, since the circle is symmetrical about the x-axis and y-axis, hence the moment of inertia possessed by the circle about the x-axis and y-axis both are equal. That means I-axis is equal to IY is equal to pi d to the power of 4 by 64, or in terms of r, it is equal to pi r to the power of 4 by 4 now. Now, the moment of inertia possessed by the hollow circle, let capital D is representing the diameter of the main circle and small d is representing the diameter of the cutout circle. The moment of inertia possessed by the hollow circle is equal to, it is the difference of moment of inertia possessed by the outer circle, that is the main circle, to the moment of inertia possessed by the cutout circle. Here it is equal to Again, this circle is symmetrical about the x-axis and y-axis. Hence, I-axis is equal to I by y, which is equal to pi by 64 of difference of d to the power of 4 to the d to the power of small, where capital D is representing the diameter of the outer circle, small d is representing the diameter of the cutout circle. For the semicircular lamina, since the area is half of the circle, the moment of inertia possessed by the semicircular lamina about its diameter, that is the AB, is given by half of the moment of inertia possessed by the complete circle, which is equal to pi d to the power of 4 by 128. Okay, in terms of, after substituting the values of pi, we got this values is equal to 0.11 r to the power of 4. Similarly, for the quadrant circle now, the moment of inertia possessed by the quadrant circle, since the area is 1/4 of the main circle now, that complete circle, hence it is equal to 1/4 of moment of inertia possessed by the circle, which is equal to pi d to the power 4 by 4 into 64 in denominator. So, which is equal to, in terms of radius, is equal to 0.2055 r to the power of 4 now. Okay, by using these fundamentals, now we can determine the moment of inertia possessed by the composite sections. Here, composite section means it is a combination of regular sections like square, rectangle, triangle, circle, semicircle, and hollow rectangular sections, as well as the hollow circular sections. Now, the taking one problem now shows a figure ABCD here given and EF, which is in the form of L section. Compute the moment of inertia of the above the area about its line KK is given now. Here KK is nothing but it is not at all belongs to the horizontal axis which is passing through the figure or extreme vertical lines now. So, it is somewhere just outside of the given composite section now. Now, after just observing this figure now, divide this figure in such a way that you should have minimum number of regular sections now. We have to divide. That means we can divide the section into like this. That is, it is treated as 1 or 2 like this. It consists of 2 sections, EF, A, and one more is if I take somewhere H and so on. That is A, F, E, H, one figure we can write it down. The second one is B, C, D, and H also. Or you can divide simply like this now. It is representing A, B, C. Here one more figure I am taking now H like this. Otherwise one more H, D, E, F and so on. That is, first of all you have to divide the segment according to our convenience into regular segments, such as it is representing each part as a rectangle, square, or triangle, semicircle, circle and so on. Now determine the moment of inertia of each segment about an axis passing through the centroid and parallel to the line KK now. That is, as the moment of inertia is required to be found out about the line KK, therefore there is no need of finding the center of gravity of the area of composite figure now. Now, the moment of inertia of the first section I am taking now, which is a parallel to the KK now. That is nothing but passing through the centroid like this now. We require. That is the moment of inertia possessed by the rectangle EFDH required now. For EFDH, The breadth is given 40 mm and height is given h is equal to 120 mm. Since it is dividing that breadth into two parts now, because breadth is equal to here now 40, the central axis we are taking, which we are taking, it is dividing the breadth into two parts now. Hence, the moment of inertia of that rectangle about the central axis, which is a path parallel to the KK, is given by h into b cube divided by 12 now. That is power 3, what we are giving the dimension should be divided by the centroidal axis now. Just we have to remember. That is hb cube by 12, where h is nothing but representing the, I am taking a convenient point h1, b1, where h1 is representing the height of the or depth of the rectangle EF HD, and breadth is representing F40 and so on. That is by using h1 b cube by 12 now. Similarly, for the rectangle 2, L is equal to length is equal to, that is breadth is equal to 240 and height is equal to 40 mm. Now, the central axis which is parallel to the KK means like this, that is which is dividing 240 into two parts. Hence, for the second one now, IG2 now, that is the second section, the moment of inertia about their central axis is equal to, we can take it as now, which is equal to 40 into 120 cube divided by 12 now. Because here now 120 is 240 is dividing into 240, dividing in two parts, and so 40 into 240 cube divided by 12. Okay, first of all we have to determine the moment of inertia possessed by the segments EF HD as well as the ABCH about the central axis passing through the parallel to the reference line KK as shown in figure now. Now we are taking the moment of inertia of first sections about the central axis, which is a parallel to the KK. It is equal to IG1 is equal to B1 D1 cube by 12, 40 into 120 cube divided by 12. It is equal to 640 into 10 to the power of 3 mm to the power of 4 now. The distance between central gravity of 1 and axis KK is equal to, which is equal to 100 into 100 plus 40 by 2 now. Here, which is equal to, it is given up to 100, the 40 by 2 now. It is given this distance is equal to 100 plus B is equal to 40 is given now. 40 by 2 is nothing but 20 now. That is 100 plus 40 by 2, it is equal to 120 mm now. That is 120 mm. The moment of inertia of first sections about the axis KK by using parallax theorem, IXS1 is equal to IG1 plus A1 H1 square. That IG1 is equal to how much value we got? 640 into 10 to the power of 3 plus A1 is equal to area is equal to 120 into 40. The distance between the two parallax is equal to 120 square, which is equal to 69.76 into 10 to the power of 6 mm to the power of 4 now. The moment of inertia of the section 2 about its central gravity and parallel to the KK is equal to, second section is there now. Already I told the moment of inertia possessed by the section 2 about its central axis, which is a parallel to the KK is equal to, how much value? 40 into 240 cube by 12 given now. The distance between KK and the axis which is passing through the center of second section is equal to 100, that is HT is equal to 100 plus 240 by 2, it is equal to 100 plus 120, it is equal to 220 mm now. That is H2 is equal to 240 mm now. So from this equation we got now, moment of inertia of the section 2 about the central gravity is equal to, which is the parallel to the kk is given by b2 d2 cube divided by 12, which is equal to 40 into 240 cube by 12. Just now I told now, which is equal to 46.08 to 10 to the power of 6 mm to the power of 4 now. The distance between the central gravity of the section 2 and the axis kk is equal to ht is equal to 100 plus. So the length is given 240 by 2, which is equal to 220 mm now. The moment of inertia of the section 2 about the axis kk is obtained by using parallax theorem. Ikk2 is equal to Ig2 plus A2 H2 square. It is equal to Igt is equal to 46.08 into 10 to the power of 6 plus A2 is equal to area is equal to 40 into 40 into H2 is equal to the distance between the two parallaxes is equal to 220 square now, which is equal to 510.72 into 10 to the power of 6 mm to the power of 4 now. The moment of inertia possessed by the L section about the line kk is obtained by taking the sum of moment of inertia possessed by each section about the kk line now. That is, Ikk is equal to Ikk1 plus Ikk2, which is equal to 69.76 into 10 to the power of 6 plus 510.72 into 10 to the power of 6, which is equal to 580.48 into 10 to the power of 6 mm to the power of 4. Okay, this is the method we have to follow to determine the moment of inertia possessed by the composite section. The similar problem we are taking now, the moment of inertia possessed by the L section, but about it, x-axis and y-axis passing through its centroid. Here this problem is, find the moment of inertia about the central axis, x-axis and y-axis of the angle sections shown in figure now. In previous case, because the centroid word is not at all mentioned, hence we are not at all determined the centroid of L section. But in this case, we have to determine the moment of inertia possessed by the L section about its central axis. Hence, first of all, we have to determine the position of centroid of L section. Now divide this L section into some number of segments such that each segment is representing in the form of rectangle, square or triangle or semicircle and so on. That is nothing but regular sections. Here according to this L section we can divide into two rectangles. Here one we are represented here 1, this is the second 2 now. Since this section is not at all symmetrical about the x-axis and y-axis, hence the line which is horizontal passing through the extreme bottom of the figure as taken as the x-axis, and the vertical line which is passing through the extreme left of the section is treated as the y-axis now. Now, after finding the position of reference axis, split the composite figure into regular section, and these are represented here as 1 and 2. The area of the first rectangle is equal to A1 we are taking, that is 100 into 20, which is equal to 2000 mm square now. The position of the centroid, that is x1, with respect to the y-axis we are taking now. It is equal to half of the 20 mm now, half of the width, which is equal to 20 by 2, it is equal to 10 by 10 mm now. Similarly, the y coordinate, that means with respect to the x-axis, it is equal to half of its height, that is 100 by 2, which is equal to 50 mm. That is, we are determining position of centroid of a rectangle having height is equal to 100 mm and breadth 20 mm now. Similarly, for the section 2, the length of the rectangle is equal to 80 minus 20 is equal to 60 mm and breadth is equal to, height is equal to 20 mm, and area is equal to 60 into 20, which is equal to 1200 mm square now. xt is equal to, that is the position of the centroid. Here the centroid lies at the intersection of the diagonal or half of the breadth and half of the height now. With respect to the y-axis. This distance is equal to here now 20 plus remaining 60 by 2 now, half of the length. That is 20 plus 30. That is at a distance of 50 mm now. That is x3 is equal to, here it is equal to 50 mm now. Here it is equal to 15. Y2 is equal to, it is half of the distance there now. That is 20 by 2 now. The distance between the center of gravity of the section and bottom face is equal to, that is, we have to determine the position of centroid now. That is y coordinate. That is, this is literally x-axis and the y-axis now. The position of centroid of L section about a line which is passing through the bottom. That is the x-axis is equal to yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2. These are the fundamental equations for the determination of center of gravity of a composite section. On substituting a1 is equal to 2000 and y1 is equal to 50 and a2 is equal to 1200 and y2 is equal to 10, we got it is equal to 35 mm now. That is, it is at a distance of 35 mm on this line it is having now. Similarly, the distance between center of gravity of the section with respect to the vertical reference line which is the passing through the extreme left of the L section is equal to xc. It is equal to a1 x1 plus a2 x2 divided by a1 plus a2. According to this figure, a1 is equal to 2000, x1 is equal to 10. Similarly, a2 is equal to 1200, x2 is equal to 50 divided by 2000 plus 1200 which is equal to 25 mm now. That is 20 width is given 25 mm. If we observe this figure now, the center of gravity is not at all lying within the object now. It is at a distance of 35 mm from the x-axis and 25 mm from the y-axis and so on. It is not at all lies within the section. Now the moment of inertia of about x-axis we have to take it. That is somewhere it is there now. Here x-axis there now. What are the coordinates are there now? Here it is given 25 and 35 now. These are the coordinates of the centroid with respect to the x-axis which is drawn bottom of the figure in horizontal. One more is the y-axis like this. Now, the moment of inertia of that entire sections about the horizontal axis, we are taking Ix1 for the first figure now, first rectangle now, which is equal to Gx1 plus A1 H1 Hx1 whole square. Ix1, it is representing the moment of inertia possessed by the first rectangle about the centroidal axis now, equal to Igx1, that is moment of inertia possessed by the first rectangle about its own central axis, plus A1, area of the first rectangle. H1 is representing the position, the distance between the central axis of the composite figure to the center of the section 1 now. The center of the section 1 is nothing but at a distance of 50 mm is there now, here now. That is the distance now becomes how much it is now? 35 and 25, it is equal to, that is a 15 mm is there now. So, here Hx1 is equal to 15 mm. On substituting where Igx1 is equal to, that is moment of inertia possessed by the first section about the horizontal line is equal to, since 100 it is dividing into parts now, it is equal to 20 into 100 x cube divided by 12, it is equal to 1.667 into 10 to the power of 6 mm to the power of 4 now. The distance between the center of gravity of the rectangle 1 now, about x-axis given by the 50, it is nothing but the position of the centroid of first rectangle with respect to the x-axis, minus 35, it is the position of the centroid of composite figure. We are taking only the positive value between them now. That is treated as h values now. It is equal to 15 mm now. Similarly, the moment of inertia of the rectangle 1 about the x-axis, that is the passing through the central axis given by, according to the Pallas theorem, Ix1 is equal to Igx1 plus A1 Hx1 whole square, which is equal to 1.667 into 10 to the power of 6 plus 2000 into 15 square, which is equal to 2.117 into 10 to the power of 6 mm to the power of 4. This is representing moment of inertia possessed by the first rectangle about the central axis. Similarly, we have to determine the moment of inertia possessed by the second rectangle about the central axis, which is parallel to its base only now. It is given by equations Ixxt is equal to Igx2 plus A2Hx2 whole square. Ixxt is representing moment of inertia possessed by the first element about the central axis parallel to its base, which is equal to Igxt is representing the central moment of inertia of second section about its own central axis. That is like this. Here we are taking it is equal to how much it is? Dimensions we are taking it is equal to 25, 35. That means it here 35. It is here it is equal to 10 is there. Difference is equal to, we are taking Hxt is equal to 35 minus 10. It is equal to now 15 mm now. Sorry, 35 minus 10 is equal to 25 mm. So Hx is equal to 25 mm. The moment of inertia here is equal to Ixxt is equal to Igx2 plus A1 H1 square. Igxt is equal to how much value we got? 60 into 20 to the power of 3 divided by 12, which is equal to 0.04 into 10 to the power of 6 mm to the power of 4 now. Similarly, Ixxt is equal to Igx2 plus A2Hx2 whole square, which is equal to 0.04 10 to the power of 6 plus area of the second rectangle is equal to 1200 into the distance between them is equal to 25 square, which is equal to 0.79 into 10 to the power of 6 mm to the power of 4 now. So the moment of inertia of L section about the central axis is given by the sum of the moment of inertia of each rectangle possessing about the central axis. That means Ix is equal to Ixx1 plus Ixx2, which is equal to 2.117 into 10 to the power of 6 plus 0.7 into 10 to the power of 6, which is equal to 2.907 into 10 to the power of 6 mm to the power of 4. This is our required answer. Similarly, the moment of inertia of the rectangle about the y-axis. About the y-axis means the axis which is passing through the central axis, but it is vertically required now. That is the coordinates are at a distance of 25, 35. That y-axis is nothing but we are moving toward the left hand side with respect to the reference of vertical line now. So we have to determine now. The first rectangle is there now. The moment of inertia lies at 20 by 2 now. That is 10 now. Here 25. The difference is equal to now becoming 15 mm now. That is by using the theorem now, Iy1 is equal to Gy1 plus A1 Hy1 square now, where Ig1 is representing the moment of inertia of the first rectangle about the vertical line now. Vertical line is nothing but here it is a passing through like this now. In which dimension is divided now 20 now. Hence 100 into 20 cube by 3 we require now. 20 cube by 12, which is equal to 0.67 into 10 to the power of 6 mm to the power of 4 now. The distance between center of gravity of rectangle 1 and y-axis is equal to 25 minus 10 is equal to 15 mm. Already just given. Iy1 is equal to the moment of inertia possessed by the first rectangle about the x-axis is equal to, it is equal to Ig 0.67 into 10 to the power of 6 plus 2000 into, the difference is given now 15 mm, that is a 15 square now. It is equal to 0.2517 into 10 to the power of 6 mm to the power of 4 now. Similarly, for the rectangle 2 is there now. The center of gravity lies at a distance of, that is x2 is equal to, what are the values we have taken now? 20 plus 60 by 2, which is equal to 50 mm we are taken now. But here 25. Center of gravity of whole section. That means the difference is equal to, when we are measuring with respect to y-axis, that is the difference of x coordinates we have to take. That is 50 minus 25 is equal to 25 mm. That is h by 2 is equal to 25 mm now. Ij is equal to the moment of inertia possessed by the second section above the vertical line is equal to, the length is given 60 and 20 is given. It is dividing 60 into 2 parts, hence it is equal to 20 into 60 to the power of 3 divided by 12, which is equal to 0.36 into 10 to the power of 6 mm to the power of 4 now. H by 2 is equal to the difference of x-axis of both the things now. One is here 10 dimensions now. It is equal to 35, which is equal to 35 minus 10 is equal to 25 mm now. So the moment of inertia of second rectangle about the y-axis is given by I y by 2 is equal to g by 2, that is nothing but the moment of inertia possessed by the second rectangle about the vertical line, plus here a2 h by 2. H by 2 is nothing but the distance between the centroid of whole section and centroid of second section. We are measuring with respect to the y-axis, that means difference of x coordinates only, which is equal to, already we have determined is equal to 25 mm. So 0.36 into 10 to the power of 6 plus area is equal to 1200 into distance is equal to 25 whole square. And simplification we got to 1.11 into 10 to the power of 6 mm to the power of 4 now. So the moment of inertia possessed by the L section about the central axis and parallel to the y-axis, that is Iyy is equal to it is equal to sum of the moment of inertia possessed by each section about the central axis, which is equal to 0.517 into 10 to the power of 6 plus 1.11 into 10 to the power of 6, which is equal to 1.627 into 10 to the power of 6 mm to the power of 4. This is our required answer. Moment of inertia of composite section. Here we are taking T section now. Now when comparing with the previous figure now, in previous figure we are taken L section, it is not at all symmetrical about the vertical line and horizontal lines. Hence we have taken the line which is passing through the bottom of the figure in horizontal is treated as x-axis, and the vertical line from extreme left position taken y-axis now. But in this figure, if we observe, it is symmetrical about the vertical line now. That is, here if you draw the lines, this vertical line is there now. It is now symmetrical line now. And hence this is treated as the position of vertical reference line now. And one more horizontal reference line is required, which is always passing through the bottom of the figure now. Hence this is treated as x-axis now, and it is treated as y-axis now. Now. That means the position of centroid of this figure always lies on symmetrical lines, that is on y-axis somewhere now. That means when we are taken y-axis means the x coordinate of the centroid is equal to 0. That is here xc and yc is representing the position of the centroid of composite figure 1 and 2. According to this figure, since it is symmetrical about the vertical lines, that means the centroid lies always on vertical line only. That is the x coordinate is equal to 0 now. So when we are taking like the symmetrical lines, we are avoiding calculation of the position of xc with respect to the some reference line now, because already we got it according to the fundamentals of symmetrical lines now. So for this problem is not required to determine the position of xc now, only yc is required now. Okay, this is the main difference between the previous problem, that is L section, as well as the T section now. Now I am reading the problem number 2 now. Find the moment of inertia of a T section with a flange as 150 mm by 50 mm and web as 150 mm by 50 mm about the x-axis and y-axis through the central gravity of the section now. That means first of all we have to determine the central gravity of composite section. Already I told now, since it is symmetrical about the vertical line, hence that is treated as a vertical axis, and the bottom line is treated the bottom of the figure in horizontal treated x-axis. Hence, since it is a symmetrical about the y-axis, the position of centroid lies on vertical line only. That means not required to determine position of x coordinate since it lies on the same thing, x is equal to 0. Only we have to determine position of y c now. Okay, first of all, since it's a composite figure now, divide this figure into segments in such a way that each segment is representing in the form of rectangle, square or rectangle, square, circle, semicircle and so on. That is the regular sections. But in this case, we are getting only two rectangles now. One is the flange, it is represented as 1. The second is the 2 as shown in figure now. Now rectangle 1, since we required the position of centroid, that is y coordinate, that is yc is equal to, what is the equation we are having? a1 y1 plus a2 y2 divided by a1 plus a2 required now. Where a1 is representing the area of the first section, y1 is representing position of centroid from the bottom of the flange. That is somewhere it is there here now. That is passing through the width of the flange now. That is 50 mm by means 25 mm. That is. But from the bottom position now, it is equal to, that is y1 is equal to 150 plus 50 by 2, it is equal to 175 mm now. That is, here h1 is equal to, we are taking y1 is equal to 175 mm. Area is equal to 150 by 50, it is equal to 7500 mm to the power of 2 now. Similarly, for the area 2 now, height is given 150 mm and 50 mm. That area is equal to 150 by 50 is equal to 7500. Similarly, here y2 is equal to, it always lies for this rectangle when you are taking, it is half of its height now, which is equal to 150 by 2, it is equal to 75 mm. That is, we can take it as y2 is equal to 150 by 2, it is equal to 75 mm. Now, I am substituting in the equations, yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2. We got yc is equal to 125 mm. That is at a distance of 125 mm. Here, this 125 mm, the center of gravity lies here now. So, this is known as the position of the centroid on vertical line, which is at a distance of 125 mm from its base now. So, I am representing here now. This is known as the position of central axis now. That is the x-axis and so on. Y-axis already we determined somewhere, it is known as y reference line now. Now we require moment of inertia about the x-axis as well now. That is for the first element, you have to determine the moment of inertia of first rectangle. Since the dimension 50 mm is dividing now, when you are taking parallel lines, so the moment of inertia possessed by the first rectangle about an horizontal axis passing through its centroid, it is equal to 150 into 50 to the power of 3 divided by 12 now. 150 into 50 to the power of 3 divided by 12 now. Now, area of the first triangle A1 hx1 square now. A1 is equal to 150 into 50. It is there. That is the area is equal to 150 into 50. The distance between these two lines is equal to, we are taking, it is equal to h1. It is at the distance of 175 minus 125. It is equal to 50 mm. It is there now. That is the hx1 is equal to 175 minus 125. It is equal to 50 mm. The moment of inertia of first rectangle about the x-axis is equal to, already we are taking gx1 plus A1 HX1 whole square, where IGX1 is equal to already told 150 into 50 to the power of 3 by 12, which is equal to 1.2625 into 10 to the power of 6 mm to the power of 4 now. On substituting these values now, IXS1 is equal to IGX1 plus A1H1 whole square, 1.5625 into 10 to the power of 6 plus 7500 into 1050 to the power of 2 now, which is equal to 20.3125 into 10 to the power of 6 mm to the power of 4. This is the moment of inertia of first rectangle about the central axis parallel to the x-axis now. Similarly, for the second one, here it is given 125 mm. It is given at a distance of 75 mm for the rectangle. Because for the second rectangle, it lies, central of gravity lies at a distance of 150 by 2 now, that is 75 mm. For whole section, it is at a distance of 125 mm from the base now. So, HD is equal to again 125 minus 75 mm, it is equal to 50 mm. That is H2 is equal to HX2 is equal to, we got it now, 50 mm. That is the 125 minus 75 is equal to 50 mm. So, GXT is equal to, that is the moment of inertia possessed by the second rectangle about central axis is equal to, when you are taking horizontal lines like this, it is dividing 150 mm dimensions into two parts, hence it is equal to 50 into 150 cube divided by 12, which is equal to 14.0625 into 10 to the power of 6 mm to the power of 4 now. On substituting IXX2 is equal to IGX2 plus A1H A2 x2 whole square, which is equal to 10 to the power of 6, that is 14 into 0625 into 10 to the power of 6 plus 7500 into 50 square, which is equal to 32.8125 into 10 to the power of 6 mm to the power of 4 now. So, IX6 is equal to, from this relationship we got, that is the moment of inertia possessed by the entire T section about the central axis, which is parallel to the x-axis, is equal to IXS, which is equal to sum of the moment of inertia possessed by the first section and second section about the central axis of composite section, which is equal to 20 into 20.3125 10 to the power of 6 plus 32.8125 into 10 to the power of 6, which is equal to 53.125 into 10 to the power of 6 mm to the power of 4. Similarly, the moment of inertia of the composite sections about the y-axis now. When you are taking the y-axis like this now, the center of first sections lies here only at a distance of, that is the coordinates I am writing here now. The coordinates are there, x equal to 0, y is nothing but at a distance of 75 mm. The center of composite section here it is there, it is equal to 0, 125. Here first section is there, again 0 and 175 now. So this already the about the exercise is completed by taking the y coordinate difference now. But when you are taking about the y axis now, that is the x coordinate difference is 0, because here 0, 0, 0. That means hy1 is equal to 0, hy2 is equal to 0 and so on. So from these equations now, the moment of inertia of first rectangle is equal to, since dividing 150 mm dimensions into two parts now, we can take it as 50 into 150 whole cube divided by 12, which is equal to 14.0625 into 10 to the power of 6 mm to the power of 4 now. Similarly, h1 is equal to 0, that is the difference of x coordinate is equal to 0. For the second rectangle again, it is there, it is dividing 50 dimensions into two parts now. 150 into 50 to the power of 3 divided by 12, it is equal to 1.5625 into 10 to the power of 4 mm to the power of 4 now. Again, h2 is equal to 0, hence the moment of inertia possessed by the composite figure about the y-axis is given by the sum of the moment of inertia possessed by the first rectangle and second rectangle about the central axis, which is equal to 14.0625 into 10 to the power of 6 plus 1.5625 into 10 power of 6, which is equal to 15.625 into 10 power of 6 mm to the power of 4. These are the required answers now. Now I am taking one more problem now. An I section is made up of 3 rectangles as shown in figure. Find the moment of inertia of the section about the horizontal axis passing through the center of gravity of the section now. An I section is made up of 3 rectangles as shown in figure now. That is 1, 2 and 3 now. Find the moment of inertia of the section about the horizontal axis passing through the center of gravity of the section. Somewhere it is there, you have to determine now. Now if we observe similar to the T section now, the object is that is I section is symmetrical about the vertical line now. Hence vertical line is treated as one reference line. Horizontal line is nothing but horizontal axis is nothing but the axis which is passing through the bottom of the figure now. That is x axis, it is known as this is known as y axis now. These are called here reference lines now. Now divide the section into 3 rectangles now. Here is the 1, it is the 2, it is known as third one now. Now first of all find the position of center of composite figure by using the principles now. That is yc is equal to, since x coordinate is already 0 because it is symmetrical about the vertical line now. Hence y coordinate is required now. That is yc is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. By using this fundamental equation, we have to determine the position of centroid with respect to the reference lines, that is the x-axis which is taken bottom of the figure in horizontal directions. And a1 is equal to 60 into 20 is equal to 1200 mm to the power of 2 now. y1 is equal to, the position is given here 20 plus 100 plus 20 by 2 which is equal to 130 mm now. For the second one, that is 100 into 20, that is 2000 mm square now. y2 is equal to 20 plus, here 100 is given 100 by 2, that is 50 mm. 20 plus 50, it is equal to 70 mm now. Similarly, for the rectangle 3 now, area is equal to 100 into 20 and y3 is equal to, that is half of the section is equal to 20 by 2 which is equal to 10 mm now. Now moment of inertia is given by, the center of gravity is given by the equations a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. On substituting the values of a1 y1 and a2 y2 a3 y3, we got the values of ic is equal to 60.8 mm now. That is the moment of inertia lies at a distance of 60.8 mm now. The moment of inertia about the x-axis is required now. First determine the moment of inertia of first rectangle now. So Ix1 is equal to Igx1 plus A1 Hx1 square now. So first figure is nothing but here it is given now. The moment of inertia, that is the position of centroid is at a distance of, it is equal to 130 mm. It is equal to 60.8. This is nothing but here 10. It is 60.8 and one more is 130 mm now. Now the difference is required now. For one more is there now. For this rectangle now 20 plus 50 70 mm it is there. This, that means this is the treated as hy2 is equal to, that is the difference between the center of gravity of whole section to the center of gravity of second section is equal to hy2 is equal to how much it is 75, that is here 20 plus 50 by 2 100 by 2, it is equal to 70 minus 60.8. Similarly here hy3 is equal to 60.8 minus 10 mm. For this one hy1 is equal to 130 minus 60.8 mm. We have to take the value, the difference of this values. So moment of inertia about the first rectangle is equal to Ix1 is equal to Igx1 plus A1 Hx1 whole square. Ixx1 means here Igx1 means representing the moment of inertia of first rectangle about its central axis, and parallel to the x-axis given by 60 into 20 cube by 12. Here this is equal to 40 into 10 to the power of 3 mm to the power of 4. Hx1 is equal to already equal to 130 minus 60.8 is equal to 69.2. And moment of inertia of first rectangle about the x-axis is equal to Ixx1 is equal to Igx1 plus A1 Hx1 square, which is equal to 5786 into 10 to the power of 3 mm to the power of 4 now. Similarly, for the rectangle 2 now, Ixx2 is equal to Igx2 plus A1 Hx1 whole square, which is equal to 20 into 100 cube is dividing into 12. So, 1666.7 into 10 to the power of 3 mm to the power of 4. Hx is equal to 70 minus 60.8, already we discussed now, this is equal to 9.2. So, the moment of inertia of second rectangle about the central axis given by Ixx2 is equal to Gx2 plus A2 Hx2 whole square, which is equal to 1836 into 10 to the power of 3 mm to the power of 4. For the third rectangle now, Ixx3 is equal to Igx3 plus A3 Hx3 whole square, where Igx3 means representing the moment of inertia of third rectangle about its central axis, which is equal to 100 into 20 whole cube divided by 12. Already we discussed this is equal to 66.7 into 10 to the power of 3 mm to the power of 4. And the distance is given 60.8 minus 10 is equal to 50.8. This point we will discuss now. The moment of inertia of rectangle third about the x-axis is equal to Igx3 plus A3 Hx3 whole square, which is equal to 66.7 into 10 to the power of 3 plus 2000 into 50.8 whole square, which is equal to 5228 into 10 to the power of 3 mm to the power of 4 now. So, the moment of inertia of whole section about the x-axis is given by the sum of the moment of inertia of each rectangle about the central of about the central axis of composite figure, which is equal to the sum is equal to 5786 into 10 to the power of 3 plus 1836 into 10 to the power of 3 plus 5228 into 10 to the power of 3, this which is equal to 12,850 into 10 to the power of 3 mm to the power of 4. This is known as moment of inertia of I sections about the central axis, which is parallel to the x-axis. Now I am taking find the moment of inertia of all sections shown in figure about an axis passing through its center of gravity and parallel to the x-axis now. Parallel to the x-axis. So here if we observe this figure now, this figure is symmetrical about the vertical axis now. That is, if I take the figure, this is known as the vertical axis, and bottom line is treated as the y-axis and shown in figure. Since this figure is symmetrical about the vertical axis, the x-coordinate to the centroid is treated as 0 now. X-coordinate is lies on vertical line only, hence it is equal to 0. We require only position of centroid of the y-coordinate of its centroid now. That is the yc required now. So fundamental equation is yc is equal to a1y1 plus a2y2 divided by a1 plus a2. By using these equations, first we have to determine the position of this centroid now. So a1 is representing the area of the first rectangle, that is the entire rectangle here now we are taking, which is equal to 300 into 200, which is equal to 60,000 mm square now. The y1 is equal to, that the position is half of the rectangle, that is 300 by 2 is equal to 150 mm. And for the cutout circle, the area is given by pi by 4 d square, which is equal to 17,670 mm square now. And y1 is equal to, here the position is centered here now, it is there, which is at a distance of 100 mm from the top is given. That is, which is equal to 300 minus 100, which is equal to 200 mm now. Since the area is now removed now, the modified equation for determination of YC is equal to A1 Y1 minus A2 Y2 divided by A1 plus A1 minus A2 is required. Here minus sign is representing that is cut out, that is area is removed now. Area is treated as negative values now. So from this equations and substituting the values, we got YC is equal to 129.1 mm. This one. So the moment of inertia of rectangular section about an axis passing through the center of gravity and parallel to the x-axis given by. So first one is we got 129.1 mm. Just I am taking that figure. Here it is at a distance of 129 like this. I think. That is, this is known as central axis now. 129.8 now. The center of rectangle is at a distance of 150 now. That is, here y1 is equal to 150. And the center of cutout circle is given. It is equal to y3 by 2, which is equal to 200. And yc 129.8 now. So the difference of y1 and y, one is treated as h2 y1. The second one is the difference between y2 and yc, that is treated as h by 2 now. So here, when you are taking the moment of inertia of whole section, when you are taking, first of all consider the moment of inertia of rectangular section about an axis passing through its center of gravity, which is equal to parallel to the, that is required central axis, that is the x-axis. Since the 300 dimension is dividing now, and so 200 into 3300 to the power of 3 divided by 12, 450 into 10 to the power of 6 mm to the power of 4. H1 is equal to already told 150 minus 129 mm, which is equal to 20.9 now. Similarly, for the second one now, that is the moment of inertia of entire section about the central axis of composite figure is equal to Ig1 xx is equal to Ig1x plus A1 and H1 square now, which is equal to 450 into 10 to the power of 6 plus 300 to 200 into the area of the rectangle. The difference value is 20.9, which is equal to 476.21 10 to the power of 4 mm to the power of 4 now. Similarly, the moment of inertia of circular section about an axis passing through center of gravity and parallel to the x-axis is given by Ig2x is equal to pi by 64 into d to the power of 4, which is equal to 24.85 into 10 to the power of 6 mm to the power of 4 now. And the difference between the center of gravity of the circle to the center of gravity of the whole section is equal to 200 minus 129.9 is equal to 70.9 mm, which is treated as H2 now. Ig2xx, that is the moment of inertia of the cutout circle about the central axis of the composite figure. It is equal to Ig2x plus A2H2 square, where Ig2x is representing moment of inertia of circle about its central axis, A2 is representing area of the circle, H2 is representing the difference between the centroid of the circle to the centroid of the whole section now. That is the composite figure now, which is equal to 24.85 into 10 to the power of 6 plus area of the circle is 17.670 plus the difference is given 70.9, which is equal to 113.67 into 10 to the power of 6. The moment of inertia of the whole section is given by, since the area is removed, area of the circle is removed, hence the moment of inertia possessed by the circle is we have to remove from the, that is we have to take it as negative values. That means 476.21 into 10 to the power of 6 minus of 113.67 into 10 to the power of 6, which is equal to 382.54 into 10 to the power of 6 mm to the power of 4. This is our required answer. So these are the some of the example we have taken the problems we discussed now. So parallax theorem generally is applicable for determination of moment of inertia of composite figure about the central axis of the composite figure. If you know the moment of inertia about the composite figure about central axis, we can transfer that moment of inertia about any axis which is passing through the, which is parallel to the central axis by using parallax theorem. This is the important of the parallax theorem for the determination of moment of inertia of composite figure about any axis. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.